Hello students, in last lecture we have talked about the monotone sequences. We proved that any increasing boundary number sequence is convergent, decreasing boundary below sequence is convergent, and we use that result to show that if Sn is 1 plus 1 upon n raised to n, then Sn is increasing and boundary above, therefore it is convergent. Now in this lecture, we'll study operations on convergent sequences. We are familiar that if f and g are two functions defined in neighborhood of A, and if fx and gx has limits L and M, then limit x tends to a of fx plus gx is L plus M, limit x tends to a of fx minus gx is L plus M, limit x tends to a of fx into gx is L into M, limit x tends to a of fx upon gx is L by M, provided gx is not equal to 0 in neighborhood of A and M also not equal to 0. Additionally, limit x tends to a of mod f of x is equal to mod L. So this is algebra of limit of function. On same line you have studied if f and g are two continuous functions at A, then their addition is addition, difference, product, quotient, scalar multiple, then mod functions are also continuous at that points, or maximum of fg, minimum of fg are continuous at those points. For derivative, for integration, those results holds. So we are going to prove that results for convergent sequences now. So if I have two convergent sequences, say Sn and Tn, then our aim is to show that their addition sequence Sn plus Tn, difference sequence Sn minus Tn, then product sequence Sn into Tn, quotient sequence Sn upon Tn if Tn is not 0 for all n, scalar multiple sequence k times Sn, and the modulus sequence mod Sns are also convergent sequences. So we will study algebra of convergent sequences or operations on convergent sequences. So what is our theorem? Let Sn and Tn be convergent sequences. Okay, what we do, first we will start to use this part. If Sn and Tn are convergent sequences such that limit n tends to infinity of Sn is equal to L, limit n tends to infinity of Tn is equal to M, then 1 limit of Sn plus Tn is equal to L plus M, limit of Sn minus Tn is L minus M, limit of scalar multiple sequence Ksn is k into L. Third, limit n tends to infinity of Sn Tn product sequence is L into M. Fourth, limit n tends to infinity of quotient sequence Sn upon Tn is L by M, where Tn is not equal to 0 for all n and M is also not equal to 0. 5. Limit n tends to infinity of mod Sn is equal to mod L. So we'll prove these results one by one. Okay. So first one, as I have to show that limit of n tends to infinity of Sm plus minus Tn is L plus minus M, means I have to show that for given epsilon greater than 0, there exists positive integer n naught such that mod Sm plus Tn minus L plus M must be less than epsilon. Okay, so for that we'll take that expression first. Given limit n tends to infinity of Sn is equal to L, limit of Tn is M is 1. What is your claim? Limit n tends to infinity of Sn plus minus Tn is equal to L plus minus M. So for this, mod of Sn plus minus Tn minus L plus minus M, this is equal to mod of Sn minus L plus minus mod of Tn minus M, which is less equal by triangle inequality mod Sn minus L plus mod of Tn minus M. We know that mod A minus mod B, mod A plus minus B is less equal mod A plus mod B. By using, we'll get this. Okay, from 1, for given epsilon greater than 0, there exist positive integers n1, n2 such that mod of Sn minus M, Sn minus L is less than epsilon by 2 n greater equal n1, and mod of Tn minus M, this must be less than epsilon by 2 for n greater equal n2. Okay, why I am taking here epsilon by 2, because here if I take this is less than epsilon by 2, this is less than epsilon by 2, then whole thing becomes less than epsilon. Okay, so from 2 3 2 and 3, mod of Sn plus minus Tn minus L plus minus M, this must be less than epsilon by 2 plus epsilon by 2 is equal to epsilon for any n greater equal n naught is equal to maximum of n1, n2. As this statement hold for n greater equal to n1, n greater equal to n2, therefore both of that statement must hold for n naught equal to maximum of n1, n2. In case of limit of functions, you are getting 0 less than mod x minus a less than delta. For given epsilon greater than 0, there exists delta 1 greater than 0 such that whenever 0 is less than mod x minus a less than delta 1 implies mod fx minus a less than epsilon. And gx tending to limit of gx is m, means for given epsilon greater than 0, there is some delta 2 greater than 0 such that 0 less than mod x minus a less than delta 2 implies mod of gx minus m less than epsilon by 2. Now, we are evaluating limit in that case at point A. So, we are finding internal neighborhood of A among delta 1 and delta 2. So, in that delta 1, delta 2, we are choosing minimum of delta 1, delta 2. Here, we are finding limit of sequences as intending to infinity. Means we are observing the closer neighborhood of infinity. So, among n1 and n2, if I choose maximum of n1, n2, and that is near to that infinity. Okay. Actually, it is not near because n tending to infinity. So, only this is the change in case of proving limit of proving results of limit of functions and limit of sequences, or algebra of continuous functions, algebra of convergent sequences. Only this is slight change. There is not any other change. Okay, on same line we are taking this adjustment there and here also. Okay. So what we proved, for given epsilon greater than 0, there exists some positive integer n naught such that mod of Sn plus minus Tn minus L plus m minus L plus minus m less than epsilon. Okay. This implies limit n tends to infinity of Sn plus minus Tn is equal to L plus minus m. Is it clear? So now we have to prove second one. Okay. On the same line, we have given limit of Sn is L. We have to show that limit of Ksn is Kl. Okay. Second, given this. What is our aim? Claim limit n tends to infinity of Ksn is equal to Kl. K belongs to R. Here also K belongs to R. That is fixed. So for this, mod of Ksn minus Kl is equal to mod K times mod of Sn minus L. Mod A is equal to mod A into mod B. By using that, we will get this. Okay. This is 1, this is 2. So from 1, for given epsilon greater than 0, there exists some positive integer n naught for given epsilon greater than 0, there exists some positive integer n naught such that mod of Sn minus L is less than epsilon upon mod K plus 1 for n greater equal n naught. I have to cancel this mod K, and that's why I am adjusting mod K here. Is it clear? Then why I am not taking just mod K? Because I have to prove result for any K belongs to R. If K is 0, then mod K is 0, and then epsilon upon mod K is not defined. And for that purpose, I am taking epsilon upon mod K plus 1. Okay. From 2 and 3, we get mod of Ksn minus Kl. This is less than mod K into epsilon upon mod K plus 1. N greater equal n naught. Okay. And therefore, mod of Ksn minus Kl, this must be less than epsilon, since mod K upon mod K plus 1, this lies between 0 and 1. So if you multiply given number by number lying between 0 to 1, resulting product is smaller than that number. Okay. So thus, for given epsilon greater than 0, there exists positive integer n naught such that mod of Ksn minus Kl is less than epsilon for any n greater equal n naught, and therefore limit of Ksn is equal to Kl. Okay, so we proved that scalar multiple of convergent sequence is convergent, and it converges to that scalar into limit of that convergent sequence. Okay. Now we have to prove third one. So in that, we have to show that limit of product of two sequences is equal to product of their limits. So we have given limit of Sn is L, limit of Tn, n tends to infinity is equal to m. This is 1. Okay. What is your claim? limit n tends to infinity of Sn into Tn is equal to L into M. So for this, as I have to show that mod of Sn Tn minus Lm less than epsilon, so I am taking left side expression for this. Sn Tn minus Lm, I can write this as Sn Tn minus, we'll add and subtract. I have to relate this to their limits. I have to use mod of Sn minus L, mod of Tn minus M. So what I'll do, I will take limit of one sequence into nth term of other sequence. So I can take it as Ltn plus Ltn minus Lm. Okay, I am taking limit of Sn sequence and nth term of other sequence. I am inserting that there. Then this will become mod of Tn. This is equal to Tn into Sn minus L plus L into Tn minus M. Then this is less equal mod Tn into mod of Sn minus L plus mod of Ltn minus Lm. We'll keep it as it is, say. Okay. Now we know that, what do we know? Every convergent sequence is bounded. So as Tn is convergent sequence, so Tn is also bounded sequence. Okay. Now since Tn is convergent sequence, therefore Tn is bounded. Every convergent sequence is bounded. Therefore, there exists some, say, p greater than 0 such that mod of Tn is less than equal to p for all n. Okay. Using 3 into, we get, what we get? Mod of Sn Tn minus Lm, this is less equal p times mod of Sn minus L plus mod of Ltn minus Lm. Okay, but p is positive, so I can take p inside, Psn minus Pl plus mod of Ltn minus Lm since p greater than 0. I will take this as 4. This as 4. Now since from 1 limit of Sn is equal to L, limit of Tn is equal to M, we know that scalar multiple sequence of convergent sequence is convergent. Therefore, limit n tends to infinity of Psn is equal to Pl, and limit n tends to infinity of Ltn is equal to Lm. Scalar multiple of convergent sequence is convergent. And therefore, for given epsilon greater than 0, there exist positive integers n1, n2 such that mod of Psn minus Pl is less than epsilon by 2, n greater equal to n1, and mod of Ltn minus Lm is less than epsilon by 2, n greater equal n2. Okay. 5. From 4 and 5, for n naught is equal to maximum of n1, n2, mod of Sn Tn minus Lm, this must be less than epsilon by 2 plus epsilon by 2 is equal to epsilon for any n greater equal n naught. Is it clear? Psn minus PL is less than epsilon by 2, mod of LTN minus LM less than epsilon by 2. And if I choose n greater or equal n naught is maximum. Okay. So thus for given epsilon greater than 0, okay, thus for given epsilon greater than 0, there exists positive integer n naught such that mod of SNTN minus LM is less than epsilon for any n greater or equal n naught. And therefore, limit n tends to infinity of Sn into Tn is equal to L into M. So thus, product of two convergent sequences is convergent, and limit of that product of convergent sequences is product of their limits. Now we have to prove fourth part. So what is fourth? Here given limit n tends to infinity of Sn is equal to L and limit of Tn is equal to M, n tends to infinity, Tn not equal to 0, M not equal to 0 for all n. Okay. Claim limit of Sn upon Tn is equal to L by M. Now we proved that limit of product of two sequences is product of their limits. So it is, I can easily write this as limit n tends to limit of Sn by Tn is equal to limit of Sn into limit of 1 by Tn. And then it will become L into limit of 1 upon Tn. So if we show that limit of quotient sequence converges to quotient of the limit of that sequence, then we are through. So for this, it is sufficient to show limit n tends to infinity of 1 upon Tn is equal to 1 upon M. Okay. Now, mod of 1 upon Tn minus 1 upon M, this is nothing but mod M minus Tn upon M into Tn. Right? Which is equal to 1 upon mod M into mod Tn into mod of Tn minus M. Okay. So for this we will give 1. Now since limit n tends to infinity of Tn is equal to M not equal to 0. Therefore, for epsilon greater than 0 or therefore for epsilon is equal to mod M by 2 greater than 0, there exists some positive integer n1 such that mod of Tn minus M is less than mod M by 2. N greater or equal n1. And therefore, mod of mod Tn minus mod M is less equal mod Tn minus M is less than mod M by 2, n greater or equal n1. Now just compare this. We know that mod of mod A minus mod B less equal mod of A minus B. So therefore we will get mod of mod Tn minus mod M, this is less than mod M by 2 for n greater or equal n1. So we know that mod x minus a less than delta implies x lies between a minus delta to a plus delta. By using that, we get Therefore, mod m minus mod m by 2 is less than mod Tn is less than mod m plus mod m by 2 for every n greater equal n1. Now we'll just take this part. We'll get mod m by 2 is less than mod Tn for every n greater equal n1. And therefore 1 upon mod Tn is less than 2 upon mod m for every n greater equal n1. So 1 upon mod Tn is less than 2 upon mod m here. Using 2 in 1, we get 1 upon mod of 1 upon Tn minus 1 by m. This must be less than 2 upon mod m square into mod of Tn minus m, n greater equal n1. This is 3. Okay. Now since limit of Tn is equal to m, therefore for given epsilon greater than 0, there exists some positive integer n2 such that mod of Tn minus m is less than. I have to cancel this 2 upon mod m square. So I will take mod m square by 2 into epsilon for n greater equal n2. Therefore, for n0 is equal to maximum of n1 n2, mod of 1 upon Tn minus 1 upon m, this must be less than 2 upon mod m square into mod m square by 2 into epsilon for any n greater equal n0 from 3, 4. Okay. This get cancelled. Therefore, 1 upon mod 1 upon Tn minus 1 upon m is less than epsilon for n greater equal n0. And therefore, limit of 1 upon Tn is equal to 1 by m. N tends to infinity. So here each term of Tn must be non-zero and m must be non-zero. Okay. Now limit n tends to infinity of Sn upon Tn is equal to limit n tends to infinity of Sn into limit n tends to infinity of 1 upon Tn, which is equal to m into 1 upon L into 1 upon m, which is equal to L by m. Hence proved. Hence result is proved. Is it clear? Now we have to prove last part. Given limit n tends to infinity of Sn is equal to L. What is your claim? Limit of mod Sn is equal to mod L. Okay. So for this, mod of mod Sn minus mod L less equal mod Sn minus L. 1. This is 1, this is 2. So from 1, for given epsilon greater than 0, there exists some positive integer n1 or n0 such that mod of Sn minus L is less than epsilon for any n greater equal n naught. So from 2 and 3, what will get? Mod Sn minus mod L, this must be less than epsilon for any n greater equal n naught. So for given epsilon greater than 0, there is n naught such that this hold. Therefore, limit mod Sn is equal to mod L as n tends to infinity. So with this we proved all the results. Now here these are just if then conditions, means converses may not be true. Addition of two convergent sequences is convergent. If sum of two sequences is convergent, does that implies that contributing sequence in that sum must be convergent? So answer is no. I can construct the two sequences which are divergent, their sum is convergent. If I take Sn is equal to minus 1 raised to n, okay, Sn is equal to minus 1 raised to n, Tn is equal to minus 1 raised to n plus 1. Then Sn, Tn are divergent such that limit of Sn plus Tn is 0, limit Sn Tn is minus 1, then limit of Sn upon Tn is again minus 1, okay, and limit n tends to infinity of mod Sn is also 1. So these are divergent sequences such that their addition is convergent, product is convergent, quotient is convergent, modulus sequence is also convergent. Means converse part of these results are not true. So with this discussion, today we'll stop here. We'll meet in next session with new topic, operations on divergent sequences and examples by using the algebra of limit of functions. Thank you. Bye bye.